Hi there. In this video, we're now actually going to be writing out the Fourier series for a few functions, periodic functions, that is. So if we just recall what the Fourier series actually is, it's f of x is equal to a naught over 2 plus an infinite sum of a variable n that starts from 1 and goes to infinity of an cos nx plus bn sine nx. So in order for us to be able to write out this Fourier series, we must be able to find these constants a naught, an, and bn. So there is a specific way in which these constants are determined. And in the last video, what we had done was that we had written out the integrals for a variety of different trigonometric functions. That's sine mx. We saw that this was equal to 0 for a period of 2 pi, with the bounds being from minus pi to pi. And we also had seen this for cos mx, also gave us 0. Then we saw when we take the integral of cos mx and cos nx, we get two different results. If m is equal to n, so if m is equal to n, then we just get cos squared nx or something like that. And if we evaluate that integral, we get pi. However, for every other value of m and n, which are not the same, so if m and n are different values, then this integral gives you 0. And then lastly, if we have, sorry, not lastly, so if we have sine mx and sine nx, and if m is equal to n, then we get pi. And if m is not equal to n, then we get 0. And then lastly, if we have cos mx and sine mx and we integrate this, then what we see that regardless of the values of m and n, if they are the same or not the same, it will give us 0. So these were the results that we had derived in the last video, where we looked at integrals of periodic functions. So if you want to remember how all these things came about, you can go and watch that video or rewatch it. So just another point to make. So these kinds of integrals are called orthogonal functions, where they give us 0. So if we have a function f of x and we multiply it by another function g of x, and we integrate that product between some interval a and b, and if we find if it gives us 0, then this is what's called an orthogonal function. So as I've stated earlier, we're going to use the results of these integrals to find the Fourier constants, and we're going to start with an. So how we're going to do that is we're going to take cos mx, we're going to multiply it by f of x, okay? So f of x is the function that we're going to find the Fourier series for. It could be any function. So for example, f of x is equal to 2x. And we're going to integrate that across our period minus pi to pi. And of course, our integral is with respect to dx. So what this means is that we can now replace this f of x, this function that we're integrating with, in the form as the Fourier series. So we're going to substitute the Fourier series in place of f of x. So that's the next step. So we have the integral from minus pi to pi, and we remember what the Fourier series is. It's a naught over 2 plus the sum, where we have variable n that starts from 1, goes to infinity, of an cos nx plus bn sine nx. And now we're going to multiply this by cos mx, and all this is being integrated with respect to dx. So let's multiply this out. So when we multiply this out, what we get is the integral from minus pi to pi of a naught over 2 times cos mx, so we write that down, So what we're going to do as well is we're going to multiply it by each term, and we're also going to split the integral. So we're going to write the integral for each term within the brackets. So we're going to say this is with respect to dx. Then we're going to find the integral from minus pi to pi of the second term. So that would be the sum of n is equal to 1 to infinity of an cos nx cos mx, because we're multiplying it, dx, and then the last term is the integral from minus pi to pi of bn sine nx, don't forget the sum. So we have bn sine nx cos of mx dx. Okay, so what we can also do is we can recognize that we can interchange this integral and this sum. Okay, so what I'm saying is that we can swap the position of this integral and this sum around, because an is a constant and bn is also a constant. So that's what I will do. It's still the same thing though. So I'm writing the summation in front, n is equal to 1 to infinity. Okay, and I've taken out an as a constant, and then I write the integral from minus pi to pi. And then I do the same here. So I write the integral first. So n goes from 1 to infinity. And I take out bn as the constant, and I integrate from minus pi to pi. So let's look at these integrals now. So you can see that we have cos nx, cos mx, sine nx, and cos mx. So these are looking very much like the integrals that we had derived. So let's look at this last integral, sine nx and cos mx. What does this equal to? So if we have cos mx sine nx, this gives us 0 regardless of if m is equal to n. So this last term of the integral is going to be equal to 0. So let's just indicate that. So this entire term is going to equal to 0. Then we have cos nx and cos mx. Okay? So let's see what that is. So we have cos mx, cos nx, and we see that we get a value of pi if m is equal to n, and we get a value of 0 if m is not equal to n. So this integral is only going to take on the value of pi for specific values of n and m if they are the same. And lastly, for the first term, we have cos mx, and the integral of cos mx, as we saw earlier, is just 0 as well. So that first term is 0. So this is equal to 0. So what are we left with? Let's substitute in some values of n. So n starts from 1, and we know that this integral is going to take on the value of 0, right? So we have a1 times 0. Then we have a2 times 0. We have a3 times 0. We can carry on like that. And at some point, since we're considering all values of n, n is going to equal m. So when n becomes m, this integral is going to take on the value of pi. And it will carry on being 0. So if we're considering the first term, the second term, the third term, that is a1, a2, a3, we can create m to take on that value of that term, and we will get pi. So if a is equal to 3, so if n is equal to 3, and then we're finding a3, then that term wouldn't be 0, it would be pi, and everything else would be 0. So that's how it actually works. So this entire integral becomes pi for that value of m. So that's the result. So what we have said is that this integral fx cos mx is equal to a m times pi. So what we can do is that we can rearrange this. We can find the value of am. Am is equal to 1 over pi times the integral from minus pi to pi of f of x times cos mx dx. So when we expanding out our Fourier series and trying to find the Fourier series, let's just say we wanted to find a3 as we've just indicated now as an example. And we also gave a random example, f of x is equal to 2x. So if we wanted to find the third Fourier coefficient a3, it would simply be 1 over pi integrating from minus pi to pi of f of x, which is 2x as the random example, and we want 3, so cos 3x. And this is a simple integral to evaluate, and we're able to find that Fourier constant like that. So we don't do it for each constant. We find a general expression for n or m, and we are able to substitute in the constants like that. So we will now do the same to find Bn. So what we'll do is we'll take the function f of x, we'll multiply it now by sine mx, and we'll integrate that between minus pi and pi. And as we had done previously, we will proceed in the same manner. We'll substitute in the Fourier series for f of x. So we have the integral from minus pi to pi, substituting in the Fourier series. So that's a naught over 2 plus the infinite sum, where n starts from 1, goes to infinity. An cos nx plus bn sine nx. Being multiplied by sine mx. Dx. So as we had done just now, we will multiply it for each term, and we will separate out this infinite sum and this integral, and we will put it into the form of the integrals that we had shown earlier. So if we do that, we get integral from minus pi to pi. We have a naught over 2 times sine mx dx, then plus we have our sum, then we have our constant an, then the integral from minus pi to pi of cos nx times sine mx. And just as was the case in the previous derivation that we did, this entire integral becomes 0 because sine cos mx nx times sine mx, this gives us 0 for regardless if n is equal to m or not equal to m. And then the last term is the sum, and we have bn, and we have integral sine nx and sine mx. It's exactly the same. So this first term also gives us 0 because of the sine mx here. So if we write this out, then we find that we only get a value for this integral if n is equal to m. So if we take different values of n, as we had done, we can have b1, we'll have 0, then we have b2 times 0, plus b3 times 0, and it could go on like that until n takes on the value of m. Then we have bm, and we'll have pi. So this integral takes on the value of bm pi. Now, if we solve for bm, then we find that we get 1 over pi integral minus pi to pi of f of x sine mx dx. So we have found those two constants. So the last one we need to do is to find a naught. So we have already derived that an is equal to 1 over pi integral from minus pi to pi of f of x times cos nx dx. So now what we want to determine is a naught, the first term in the Fourier series. We just make n equal to 0. So we have 1 over pi integral from minus pi to pi f of x and cos of 0 essentially. Let's substitute it. So cos of 0 is equal to 1. So what that becomes is 1 over pi, the integral from minus pi to pi of just f of x dx. So these are essentially the three relations we need to determine the Fourier constants. So I think this is best illustrated in an example, and that's what we're going to do now. This is the example that we're looking at. We have a periodic function. So from minus pi to pi over 2, minus pi over 2 that is, the function is taking on the value of 0. And then from minus pi over 2 to pi over 2, the function is taking on the value f of x is equal to 4. So it's a constant y value. And then from pi over 2 to pi, it's again taking on the value 0. So our period is from minus pi to pi, and we're going to find the Fourier series between this region. So if we were to describe this function analytically, what we would say is that f of x is equal to 0 between minus pi and minus pi over 2. F of x is equal to 4 between minus pi over 2 and pi over 2. And f of x is again equal to 0 between pi over 2 and pi. And we state that it's a periodic function by saying that every 2 pi repeating units, this graph will take on the value of f of x as we have defined it. So we are now going to find the Fourier series for this illustration. As we had derived earlier, we can just go back to it. We saw that a naught is equal to 1 over pi times this integral. So that is the first thing that we're going to determine. So let's just write it again. A naught is equal to 1 over pi times the integral of minus pi to pi of f of x dx. So now we're going to integrate between minus pi and pi and put in each value of the function between these integrals. So we have 1 over pi, and then expanding it out, we have firstly the integral from minus pi to pi minus pi over 2, and that value is 0. Then we have the integral from minus pi over 2 to pi over 2, and that value is 4. And then lastly, from pi over 2 to pi, and that is also 0. So the integral of 0 is just 0, so we don't need to waste our time with that. So what we're left with is 1 over pi, and we have the integral of 4, so that is 4x being integrated from minus pi over 2 to pi over 2. So we have 1 over pi into, if we substitute pi over 2, we're going to have 4 divided by 2. So that just gives us 2. So we're going to have 2 pi. And the minus will give us a plus. And again, 4 divided by 2 is 2. 2 pi plus 2 pi is 4 pi. 4 pi divided by pi is just going to give us 4. So A naught is equal to 4. So we have essentially found the first term of the Fourier series. So now we can proceed with the rest of it. We can refer back to the derivation, and we can see that the an term is equal to 1 over pi, integral from minus pi to pi of f of x times cos nx dx. And we can do our substitutions as we had just done it. So we have 1 over pi, and the integral from minus pi to minus pi over 2 was 0. So we have 0 cos nx. Then we had integral from minus pi over 2 to pi over 2, and that was 4. F of x took on the value of 4. We had 4 cos nx. And lastly, we had pi over 2 to pi, and that was 0 again. Let's just remind ourselves once more. 0, 4, and 0. And this is the derivation that we had used, that we had developed. So this first term is going to give us 0. So this term is also going to give us 0. And we're left with the second term. So we have 1 over pi. And we can integrate it. The integral of cos is sine. So let's just take out the 4 as well. Take the 4 out. So we have 4 over pi. And we can integrate cos nx. So the integral of cos is sine. So we have sine nx over n, and we are integrating that between minus pi over 2 and pi over 2. Okay, so we can proceed with that substitution. So we have sine of n times pi over 2. Let's say n pi over 2 over n, and then minus sine of minus n pi over 2 over n. So here we need to just remember a trig identity. So the trig identity is that if we have sine of, let's just say, minus 90 degrees, or sine of minus pi over 2 radians, this is actually equal to minus sine 90 degrees, or just minus sine pi over 2. So essentially this term is minus sine and pi over 2. So if we bring out the minus, we can have a minus here and a minus here, and it's going to give us a plus. So what we'll do is we'll write plus here, and we'll remove this minus here. So these two terms are essentially the same, and we're adding them. So 1 plus 1 is 2, so 4 times 2 is 8. So what we're left with is 8 sine n pi over 2 divided by pi n. So now we just need to understand how we can get these coefficients out of this result. So this is a general result for an. So this is what an is equal to. What we would do is we would now consider different values of n. We can consider even numbers and odd numbers. Let's just say we consider even numbers. So that would be n is equal to 2, 4, 6, etc. So let's just remind ourselves what the sine graph looks like. Okay, so we start off at 0, reach 1, we go down to minus 1, then it repeats itself like that. So that is 0, that is pi over 2, that's pi, so that's 3 pi over 2, and this is 2 pi, that's 2 pi, and this is 5 pi over 2, and this is 3 pi. There's 3 pi here, and this would be 7 over 2 pi. Sorry, 7 pi over 2. So we can carry on writing like that. So if we have even numbers of n, what is going to happen? So let's just say n is equal to 2, right? So we substitute 2 here. So we can have 2 pi over 2, the 2's will cancel off, and we'll essentially have sine of pi. And sine of pi is 0, okay? So this entire term becomes 0. So an will become 0 here. If we substitute 4, we'll have 4 pi over 2, so 4 divided by 2 is 2, so we have sine of 2 pi. So sine of 2 pi is also 0, so you can see that there's a trend, and all of these things will be equal to 0. So for even numbers, we can generalize this and say that an is equal to 0, okay? So now what we're going to do is consider this for odd numbers. So n will take on the value 1, 3, 5, 7, 9, 11, and so on. So let's just say n takes on the value 1. So we have sine of just pi over 2, and sine of pi over 2 is 1. So when n is equal to 1, this value an takes on the value 8 over pi n. And let's just say we substitute 3. So we have sine 3 pi over 2. Sine of 3 pi over 2 is minus 1. So we're going to have minus 8 over pi n. And if we substitute 5, we have sine of 5 pi over 2. Sine of 5 pi over 2 is 1. So we're going to have 8 over pi n. And then if we substitute n is equal to 7, so we have 7 pi over 2, we can see that it's minus again. So we have minus 8 pi over n. So this will continue like that. So what we see is that for every alternate odd number, we have positive coefficient. We have 8 pi over n. And for the remaining ones, we have minus 8 pi over n. So what we can see here is that, so we'll say for n is equal to 1, 5, 9, etc., then an is equal to 8 over pi n. Then for n equal to 3, 7, 11, etc., an is equal to minus 8 over pi n. So we are now almost done. We are literally almost complete with writing our Fourier series. There's just one other term that we need to determine, and that is Bn. And we had derived this earlier as well. We can just show you where. So we had done it here on the top. We had seen that Bm was this expression here. So that's what we're going to use to find that term. So Bn was equal to 1 over pi times the integral from minus pi to pi. Then we had f of x and sine nx. So we substitute this in. For the function that we have considered, we're taking the integral from firstly minus pi to minus pi over 2. Let's just remind ourselves once more because it was a little while back. Minus pi to minus pi over 2, 0, then 4, and then 0 again. So we had 0 sine nx, then plus from minus pi over 2 to pi over 2, we had 4 sine nx, and lastly from pi over 2 to pi, we add 0. Okay, first and third term will disappear as they are 0, and we have 4 sine x. We can bring out the 4 in the front, so we have 4 over pi. And we integrate. Integral of sine is minus cos. So we have minus cos nx over n, and we're integrating from minus pi over 2 to pi over 2. Okay, we don't need to proceed any further because we know that cos of pi over 2 is equal to 0, and so is cos minus pi over 2. And for all multiples of that, it will give you 0. So this is equal to 0. So what we're saying is that there are no Bn terms. Bn is just equal to 0. So we can write our Fourier series. There will be no sine terms in our Fourier series. There will only be cos terms. So there are ways in which we can decide whether we can need to actually evaluate some of these integrals. And it depends on whether it's an even and odd function and some combination of it. And there is some upcoming videos in this series that will actually identify and assist you to be able to see how you can simplify the calculations just by identifying if it's an even or odd function and some combination of that. So anyway, writing out our Fourier series. we have f of x is equal to a naught over 2 plus our infinite sum starting from 1 to infinity of an cos nx plus bn sine nx. So we know that this bn is equal to 0. We had just shown that. We're only going to have these cos terms. And a naught, if you remember, was equal to 4. And an, we had seen that it actually depends on odd numbers only. And every alternate odd number was negative. So let's just go back to that. So here was a naught, and we had seen that is equal to 4. And an, we had seen that there are no even numbers. There are no even number coefficients. And for the odd numbers, we had 8 pi over n and minus 8 pi over n. So we will just substitute all of those things. So we have 4 over 2, that just gives us 2. And we can say plus that 8 over pi, we can bring it out as a common factor. So this is the 8 pi we're talking about. We'll just bring that out as a common factor. So we have 1 over n. So let's just refer to it on the top here. So when n is equal to 1, we have a positive number of this coefficient. So we have 1 over n there, so that's 1 over 1. So we have just cos x. Remember, it's cos nx, n is equal to 1. And remember, even numbers was just equal to 0, which we had shown. So now we go to 3. And 3, we see we have a negative number. So we have to write minus 1 over 3, because it's 1 over n, cos 3x. And then we now need to substitute in 5. And 5 we see is a positive. So we have 1 over 5 cos 5x. So I think you can see where this is going. We can continue in that manner. So we just change it from plus, minus. So we have minus 1 over 7 cos 7x. And we can continue like that. So this is essentially it. This is the Fourier series. We have written the Fourier series for our first function. So thank you for watching. In the next video, I will do another example, and I will also look at something called Dirichlet conditions. So this essentially tells us for what functions we can actually write Fourier series for. So thank you very much.